In this video, I'd like to talk about Fermat's principle, which is the idea that light will take the path that requires the least amount of time. And by looking at this principle, we can in fact derive Snell's law that tells us exactly how a ray of light is going to refract as it moves from one medium to another. What I've drawn out here is the general case where we examine refraction. In this case, we're going to move from a fast medium on the left-hand side into a slower medium on the right-hand side, which means we're going from a less dense to a more dense medium. This could be air to water or some other material. What we're looking at is light going from point A, which is here, to point B over there. It's going to follow this path we know, and let's look at how we figure that out. And all we really need to do is assume that we're going to travel along some distance here in the fast medium at some angle, and then we know that we've got some, we can call this horizontal distance there, and then we're going to travel at some angle in the slower medium, and so we also know we're going to have some horizontal distance, and then overall we're going to have this vertical distance as well. And so these have all been given labels, A being the horizontal distance from point A to the edge of that first medium, and B being the horizontal distance from that boundary into the slow medium out to point B. And D is our distance in the other dimension here. So the very first thing we want to write down is, well, what's the expression for the time needed to go from A to B? Well, this is going to just be our standard equation for speed and a little bit of geometry. So our time is going to be equal to, well, remember that time is equal to distance over velocity, or distance over speed, depending on what you need. And in this case, our distance, well, let's break our distance up into two parts because we have two different velocities. So we're going to have kind of time within the first material, and then we're going to have time in the second material. And so that means that we're going to have a distance 1 over a velocity 1 plus a distance 2 over a velocity 2. Okay. So let's now substitute in some values for distance. Well, what is our d1? Our d1 is this distance here. And we can get that value by looking at, well, we need to make one more note here on the distances. Let's call that kind of vertical distance x, going just from point A in that dimension up until that normal line. Okay, so if we do that, now we can say that the time is equal to the distance of a squared plus x squared, all with the square root. And that's going to be over v1, velocity in that first material. And then we do the same on the other side, but in this case, when we're dealing with this distance, we're going to put this part, this vertical part, in terms of the total distance and x. So that looks like this. So we're going to have b squared plus, and it's going to be d minus x squared all over v2. Now that we have this expression, which describes the amount of time needed to go from A to B, we want to then find the minimum by taking the derivative. Okay, so let's take the derivative. So it's dt by dx, because what we're interested in is the path, the dt, the dx, and what we want to minimize here is t. So if we do that, well, let's remind ourselves in general what that derivative form looks like. So let's just zoom in over here and say, well, let's say we've got d dx of a squared plus x squared. Okay, so what does that look like? Well, another way to write this would be d dx of a squared plus x squared to the 1/2. And that's probably a form that is a little bit more convenient to apply our differentiation. So there we have it equal to, well, we'll pull the 1/2 down, and we have a squared plus x squared, and then it's negative 1/2, and then the derivative with respect to x of the contents inside that bracket, which is 2x. And so the derivative of this form is going to be x over a squared plus x squared under the square root sign. And so that is how we're going to do both terms. So the first term is then going to be x over square root of a squared plus x. And we also have that v1 term, so let's not forget about v1. And then the next one is going to be very similar, but instead of x we have d minus x, but the form is identical. So we're going to have d minus x, but the way this works out, we actually have a negative sign because the derivative ends up producing this negative sign because of the way that we've defined d and x. Okay, so we have a negative sign here, and then we have our b squared plus d minus x squared. And then, of course, we have our 1 over v2. And so we can probably rewrite this to be just a little bit easier to read. So we'll go dt dx is equal to x over, let's put the v1 here and write this out, a squared plus x squared, and then this will be minus, and this is going to be d minus x, and we'll put the v2 out front and have b squared plus our d minus x squared. All right, so now we have an expression that tells us the dt dx. Now, we need to simplify this a little bit if we want to work with it effectively by recognizing that there's something else we can do here. So recognize sine theta is equal to opposite over hypotenuse. And so we're going to sub in, the fact that sine theta 2 is going to be equal to, well, let's think about this geometry here. Sine theta 2 is going to be equal to, well, the opposite is here over the hypotenuse is there. And in fact, sine 1 as well, we can have an equation for, because the opposite will be, again, we've got this information about all the sides. And so we're going to use that relationship here to say that, well, sine theta 2 is d minus x over this b squared plus d minus x squared square root. And we also know that sine theta 1, we can have a similar argument and say, well, that is really x over square root of a squared plus x squared. So just to go back to this, to make sure we're drawing that conclusion clearly, we have theta 2 is equal to sine, so we've got, this is d minus x, so the whole d minus the x part, divided by the hypotenuse, which we already worked out is this b squared plus d minus x squared is equal to that line there. And we do the same thing for the other side. So that's where our terms for these sine theta equations are coming from. So once we recognize that, and we go back to our equation that we have for dt dx, we realize that, in fact, that's all there. We have this is this, and all of this is that. And that's the key leap here to make, because now we substitute that in, and let's just divide this up. So once we substitute that into this equation, we get a dt dx, and we know that's equal to 0 because we're looking to minimize that, and that's going to be equal to sine theta 1 over our v1 minus our sine theta 2 over v2. And then we can bring the sine theta 2 over v2 over to the other side. And we end up with an expression where we have v1 sine theta 2 is equal to v2 sine theta 1. Great. Now let's do one more thing here off to the side and remind ourselves what the relationship is between velocity and the index of refraction. So recall that the index of refraction is by definition the speed of light in a vacuum, or c, over v in some medium. And so v1 is actually equal to c over n1, and v2 is equal to c over n2. And so if we substitute those in, we end up with an equation that should look quite familiar, which is n1 sine theta 1 is equal to n2 sine theta 2. And that is Snell's law. And that's it. That's how we derive Snell's law from Fermat's principle, just by setting up and analyzing some geometry.